Hemoglobin variants occur when there are mutations to the genes that code for globin chains. These globin chains are the protein subunits that make up hemoglobin. Genetic mutations that initially give rise to these variants can also then be passed down to subsequent generations through ordinary inheritance. In fact, hemoglobin variants are the most commonly inherited genetic disorder. They are fairly common in today's population, affecting between 7 to 10% of individuals, depending on the specific region of the world. Most common hemoglobin variants have little or no impact on patient health when inherited in the trait or heterozygous fashion. These are people who have a single abnormal gene copy inherited from one parent with a normal copy inherited from the other parent. They are usually asymptomatic carriers who do not manifest more than mild clinical features of variant. However, some individuals inherit abnormal genes from both parents. When the same abnormal gene is inherited from both parents, it results in the homozygous state, which may have severe clinical implications. There is even a chance of inheriting different abnormal versions of the same gene from each parent, a compound heterozygous state in which different mutations to the same gene are inherited. The interaction of different hemoglobin variants may have no clinical implications or may have exacerbated clinical consequences beyond even the homozygous state. In either case, these individuals are at higher risk for their offspring to inherit such a hemoglobinopathy. Historically, some hemoglobin variants were more common in certain populations due to environmental factors. The best understood of these concerns hemoglobin S, the most common hemoglobin variant. It is associated with sickle cell disease, which arose in regions where malaria was endemic. Although the disorder arising from the homozygous hemoglobin S state, sickle cell anemia, was likely to reduce overall survival, individuals who inherited hemoglobin S trait had a degree of protection against the malarial infection, exhibiting much milder disease states and being much likelier to survive. This ensured the retention and spread of hemoglobin S through to modern-day populations. Other common hemoglobin variants are hemoglobin C, associated with Western Africa, hemoglobin E, associated with people of Southeast Asian descent, and hemoglobin D Los Angeles, most commonly found in people of Indian origin. Today, there are more than 1,000 hemoglobinopathies documented, and novel forms are still being discovered. As populations continue to interact and the global landscape changes, the distribution of hemoglobin variants in various locales has continued to fluctuate in response to both historical and contemporary factors. The nature and properties of a specific hemoglobin variant are determined by the specific mutation to the globin gene. Some mutations result in hemoglobins that function normally, while others may have altered oxygen binding characteristics, altered stability, altered hydrophobicity, or other unique properties. Production of the affected globin chain may also be affected, resulting in a condition called a thalassemia, where a patient's genes are unable to make enough globin chains to support normal hemoglobin levels. The clinical consequences of hemoglobin variants vary widely, ranging from the benign conditions to severe hemoglobinopathies such as sickle cell disease or various types of thalassemias. Let's explore the health impact of these mutations and how these hemoglobin variants can be identified.